Rohini was somewhere between a mentor and a friend. So I heard about her for the first time when I was doing my bachelor's, and we had this professor called S.H. Patil, whom you might have heard of, who used to tell that particle physics is a very difficult subject. You should only do it if you are as good as Rohini Godbole. She was a student in the same department sometime back. Anyway, so I ended up doing something in particle physics. And of course, Rohini and I had very great physics discussions. She of course did a lot of what we call high energy colloidal physics, and I was involved mainly in flavor of neutrino physics. So our direct overlap was kind of less, and by direct overlap I always define in terms of which web working group you are a participant of. So we always used to be in complementary working groups, and our discussions were always in the middle, but she always implored me to try do work on high energy colloidal physics somewhere. So actually it was a surprise for me when I went back and saw how many papers we have together, and we have only one. And it was a surprise to me because we interacted so much that it was very surprising that we have only one. But yes, I'll talk about that. But we did have a lot of interactions because of her involvement in community affairs or community engagement. So she was very good at getting you roped into things. We used to call her the "can you lady." You get a phone call saying, "Amol, can you do something, and she managed to get me into working for ACRC school, ape-shaped schools, the IUPAP. I managed to get her into our program called Vigyan Vidushi, and of course she was instrumental in starting this Rahul Basu Base Series Award. She was a strong supporter of the India-based Neutrino Observatory, in connection with which we had a lot of interactions. She was one of the inducers of the Mega Science Vision 2035, which is coming out. I think Atul was also one of the inducers who started this program. And one of the things that we collaborated on, and we actually wanted to do more, was writing of popular science articles in Marathi. But we were starting the program, but somehow never went much farther. So our one paper together, Intishwari, was a sort of last ditch attempt to save the fourth generations by saying that they should be heavy Higgs. And the idea was quite simple. Idea was just that if you look at the oblique parameter T, which we essentially ruled out fourth generation later on, if you look at fourth generation, it has this contribution which is given by some functions. All of these are positive functions. So therefore delta T4 is always positive. Since S34 is mixing with the 3 generation, expected to be very small, so this term is small compared to the others. On the other hand, if you have a heavy Higgs, it also contributes to the T parameter, but now with a negative sign. So the hope was that the heavy Higgs can compensate for the fourth generation contribution somehow, and the model can be saved. We of course failed miserably in this. Of course at that time the regions were allowed because Higgs was up to 600 was already forbidden, but beyond that we said there are these nice green regions which we can look for. The last version of this paper on the archive is actually on 3rd of July 2012, okay? Because we knew that next day is going to be gone. Anyway, so that's past, but now let's look at the future, right? So of course we all know that standard model should be looked upon as an effective field theory, right? We don't go to now very particular models like fourth generation, but look at everything that can be at high scale and try to describe that by field theory. This audience doesn't need to be given the reasons why we look for things beyond standard model. Okay. So the two approaches, one was the top down, where you start with a UV model and calculate these consequences, and the second is what I'm focusing on now, where you stay agnostic to UV model but not see where data tells you. Okay. That's where the effective field theory is coming to play. Okay. So we describe the physical systems at a given energy. We include only the relevant degrees of freedom that are available to us at the low scale, but then effects of these extra degrees of freedom, which are now integrated out, are included by systematically organizing higher order terms. That's the standard effective theory that people all work in terms of is what's called SMEFT, or standard model effective field theory. This uses has the same gauge symmetry as standard model, SU3, SU2 cross U1. Higgs sector is, as you know, is SU2 doublet, and electroweak symmetry is linearly realized. One of the competing theories to this is what's called as a Higgs EFT. Now in Higgs EFT, the explicit gauge symmetry is actually only SU3C cross U1 electromagnetic. Higgs sector has a Higgs boson which is SU2L singlet, and the three Goldstone fields phi1, phi2 and phi3 transform non-linearly under SU2L. Okay, now this is again effective field theory which still stays valid. So electric symmetry in this is realized in a non-linear manner. Whatever theory at the high scale is, at low energies we get low energy effective field theory, okay, which again we are all familiar with. It's relevant at the energy scales of the order of MB, since I deal mainly with flavor physics. That comes up very handy for me. So from these two theories, you have to integrate out top quark, W plus minus and Z, and again, as we know, the only explicit gauge symmetry here is SU3 cross U1 electromagnetic. So if you want to look at the effective operators, the kind of thing you will see the following. In SMEFT, since you do want to keep SU2L intact, the left-handed fields will always appear as doublets. So this Q and even this L are doublets, because these are all left-handed fields. On the other hand, if I want to write down similar operators in the HEFT, or in fact also in LEFT, I will have to write them down in terms of D and U quarks, U type quarks separately, because SU2L is not explicitly present. Okay. These are the neutral current operators, these are charge current. Same operators will be present in HEFT except the ones involving top one. Now note that although you see this in a very compact manner, actually these are a lot of operators, because all the operators will have indices alpha, beta, ij, each of which go from 1 to 3. Alpha, beta stand for the family index of for example these leptons, and ij stands for family indices of the quarks. So actually these are indeed a lot of operators. We can do some counting. So SMEFT actually ends up having 1161 distinct operators. HEFT has about 3384 distinct operators, and all the operators here can be written in terms of these 3384 operators. Both of them finally give rise to the low energy effective field theory, which has some 3240 operators. So now, suppose SMEFT is a valid theory, it means that all the observations here should be able to be explained in terms of SMEFT, which means that information about these 3384 operators lies in this 1161, which means there should be 2223 relations among the operators, which are simply a part of predictions of SMEFT. In this particular talk, I will only focus on what's called a UV4F theories, which means only the 4 fermion operators in new physics are present. So questions we ask at this stage are the following. Can all new physics be encompassed by SMEFT? If you only focus on analyzing new physics signals of SMEFT, will we be missing some new physics signals that we should have seen? And third question is, of course, how to identify physics beyond SMEFT by experiments. No, these are only semileptonic operators. Okay, so of course this work has been done by many people over the last many years. There have been celebrated papers by Alonso Greenstein, Jenkins Manohar, Grelio, and so on and so forth. I will not go into this. So how do we deal with this? So firstly, we have to do matching between these and these operators. Not a very hard job, except for the fact that we have to consider that we would like to write these operators in terms of mass basis, because finally we want to connect them to the LEFT operators, which are written in mass basis. Yes, HEFT actually gives us a choice to write in terms of either flavor or mass basis, but we do finally want to come to LEFT, so we write this in mass basis. So first thing we do is, of course, convert mass basis to flavor basis, and that's not a big deal. All of us know that we can rotate the U and D quark mass matrices so that you can diagonalize the mass matrix of this. But note that the individual mass matrices, individual rotation matrices of U and D are not well defined, because we don't know what are the actually flavor states. Only this combination of VCKM, which is VU dagger VD, is the well defined quantity. If you go back here and try to connect these two, since you have to apply mass transformations to make it flavor, you get relations which look like this. Don't go into the messing the relations of this. Just note that these operators, which are curly C's, are SMEFTs, and these ones are HEFTs. You see that the relations between them actually you involve VU, dagger VU, which, as we just now said, is dependent on the basis. Okay, so these relations are not directly useful to us unless we have a convention. However, what turns out is the following. So we saw the relations among these Wilson coefficients depend on flavor basis, but the relations among these HEFTs, which are induced because of these relations, are not basis dependent. And that's the reason you can actually find relations between Wilson coefficients of HEFT operators that do not depend on the flavor basis. Okay? And that is the main work that I am talking about. So for example, if you want to write the operators in which all the quarks and leptons are left-handed, then you get relations that look like this. You notice that you have V here, which is VCKN, so therefore basis independent. This U is UPMNS for lepton sector, basis independent, and therefore these relations that you get are actually basis independent. Again, because of these many indices, although this is one relation, it actually are 81 relations. 45 things are CP conserving, but that's not very, very crucial. So if you do the whole hang bag of weight, you actually end up getting all the 2, 2, 2, 3 relations that we actually were looking for. We knew they should exist. The question was what they are, and turns out that they can be written very nicely in terms of, I think, about a few categories that look quite nice. Okay, lot of algebra. What useful is this exercise? So firstly, for UV4F kind of theories, the HEFT Wilson coefficients that we had and the LEFT ones, they differ only by RG evolution and the presence or absence of terms with top one. Okay, so that means that the relations that we had with HEFT can be written approximately as the relation with LEFT with proper RG evolution. That allows us to put direct bounds on many of the Wilson coefficients. So for example, this is C. Nu DLL means a nu DD kind of operator with both of them having left-handed. This gives you flavor indices. So this can be constrained by, let's say, K to pi nu nu, and this can be constrained by D to nu nu or something. This is something that we already knew. This was nothing great. However, what our relations allow us to do is that they allow us to write down Wilson coefficients on which direct bounds are very, very weak in terms of Wilson coefficients on which bounds are strong. So you could, for example, write one Wilson coefficient which is weakly constrained is equal to summations of some linear combination of Wilson coefficients which are strongly constrained. Okay, and that actually helps us doing many things. So for example, you see this relation which was there on the last page. Now this has 6 Wilson coefficients on each side. 3 are complex and 3 are real. So this equation has 18 parameters. Now 6 of these relations are complex, so which means it corresponds to 9 real linear equations. Okay. So which means that out of these 18 Wilson coefficients, or 9, let's say 18 parameters, if 9 of them have been constrained already, then other 9 can be constrained and allowed to have reasonably strong bounds. Just one of the examples. So for example, if you want to look at indirect bounds on Wilson coefficients of these kinds of operators, you will see, so this faint green or bluish circle that you see are direct bounds, whereas the green band that you see look like indirect bounds. Okay. So indeed, there are certain things that we can say by indirect bounds which was not accessible to the direct bounds. There are questions that you can ask from this observation, for example. So I observe that the imaginary part of this particular Wilson coefficient actually seems to be 0. Turns out that the relations that we get tell you why it should be 0, although the direct bounds have not been able to consider it to be 0, and the answer simply comes out of what are the relative CKM phases between these two objects. Okay. Many other quantities, for example, these green ones, the ones which are not constrained earlier, can be constrained by indirect constraints, and sometimes direct constraints here can be reduced to as much as this small number by using indirect constraints. Okay. So this actually involves a mixing of things like meson decays, neutrino oscillations, top production, high PT lepton searches, will be used to do this. Okay. Again, just an example to show that you could do this for charge current Wilson coefficients in terms of neutral current. Implications. Now that we said that new physics Wilson coefficients of different operators can relate to each other, we can go to the anomalies that we observed at experiments. What are the implications? And one important thing that this gives you is that anomalies don't come alone. Okay? How do you show that? Let's take an example. Okay, this is the relation that I showed you earlier. Don't go into details, just look at the broader picture. Now these are 6 linear equations, okay, and therefore these are linear. So you can express any 6 of them in general in terms of the other 6. Okay, that's linear algebra 101 for us. So forget about details. This means that C7, C8, C9, C10, C11, C12 can be written in terms of linear combinations of C1 to C6. All these coefficients are functions of CKM elements. Okay. Now what does this tell you? This tells you that if any one of C1, C2, C3, C4 has been found to be non-zero, which means that you have found one anomaly, it tells you that, naively speaking, all 6 of these on the left hand side would be non-zero, and which means that you should have about 6 more anomalies. Okay? Now you'll say, okay, you are being too generous, maybe some of these things cancel. But if some of these cancel, which means that at least one other should have an anomaly, and the reason they exactly cancel would imply that there is some kind of symmetry between these Wilson coefficients, and that tells us something more about new physics that we are going to look for. Okay? So in fact, what it allows us to do is it allows us to connect different kind of processes. In fact, in the context of this meeting, maybe you'll observe that many of the processes are such that one is high energy and one is low energy. So see, for example, here, well, now this is LFV K2 mu mu, you will find LFV B decays and top decays to dineutrinos. You will see things like the LFV processes lepton nucleon to lepton prime nucleon connecting with K decays. You will see charge current decays of B mesons connected to lepton sulfur decays. Here you will see lepton sulfur top decays connecting to B physics, to B decays, to dineutrinos, so on and so forth. We have 2 anomalies that still survive. One is B to K nu nu, whose possible explanation, for example, is that the operator O nu d LL actually has non-zero Wilson coefficient, and this implies that there is a possible excess that we should find in the decays of top going to dileptons or with the C quark or U quark. Another set of relations would imply that you will find an excess in the decays of B going to CL nu and B going to UL nu. So this excess necessarily implies excess in these channels, and that gives us a guidance about which channels to look for if you want to confirm anomaly in one channel. Similarly, if you look at RD star, you get explanation that will imply that you get new physics in B to D tau tau, S tau tau, or in B decays to K star tau tau, K star nu, etc. So this gives you a guidance if you observe anomaly in one channel to figure out where we should go. Okay. So of course it's not true that if you find something in one, you have to find something in the other, because they come multiplied by CKM at C coefficients. So you do have to worry to only keep those terms which have high CKM coefficients and so on. So the question there? Yes. So all these C's are new physics coefficients, right? So therefore, if one C is if the C is non-zero, would imply there should be an anomaly. Whether anomaly is observable or not will depend on the particular CKM matrix element that appears with the Wilson coefficient. So after this thing, you have to go back and look at numbers as to what matches. Yeah, this is true. This is only with dimension 6. Yeah. Once you into dimension X, of course, problems start arising. Yeah. So this is of course a start of a program. So this is yes, indeed. Yeah. So this is true. Sorry, perhaps I missed saying that. Yeah. This is only by considering things up to dimension 6. Indeed. Of course, what's more interesting is that a violation of SMEFT relations would imply physics beyond SMEFT. Okay, and I'll just show you two channels where it can be done very, very intelligently. For example, the process called B to K star tau tau, which involves the neutral current process, B going to H tau tau. Now, for those who are familiar with this, you realize that you can have new physics contribution through operators called as the scalar and pseudo-scalar operators. Some of the conditions that we saw earlier, it was this one, which you may not have noticed in this huge table that I showed you, but this implies some very simple relations. It implies that the coefficient of scalar and pseudo-scalar in this particular process have to be related by negative sign, whereas the coefficient of CS prime, which involves right-handed instead of left-handed cross, is related by a plus sign. Okay? And in fact, to do this, angular distributions of B to K star tau tau end up being very important, among which these three coefficients are relatively independent of the hadronic errors that you get and become efficient discriminators. Another way of doing this is to look at the decays of B baryons. Okay. Again, this is a decay of lambda B go to lambda C tau nu, and this ends up having operator called as OVLR, which looks like this, and this operator cannot exist in SMEFT up to dimension 6. As a result, if you find signals of this operator in a decay process, then indeed that will be a signal beyond SMEFT. Right? And this could be found in the decay process that are mentioned here. Again, there are angular coefficients which are efficient discriminators. This is again a more quantitative thing that we can do. Okay, so let me summarize. So SMEFT implies various relations among Wilson coefficients of HEFT and ADFT. They are independent of SMEFT basis chosen, and in fact all of them can be identified, at least in semileptonic. They can be used to get stronger indirect constraints on various Wilson coefficients. Anomalies should come in groups and not separately, and in that sense anomalies in meson decays, high PT searches, top decays, Z-pole observables, lepton flavor violating searches, and neutrino non-standard interactions actually are related to each other by the exclusive relations. The relations are observed to be violated. Of course, there is physics beyond SMEFT. So potentially it's possible through various angular distributions, and what it would tell us is perhaps it will test the nature of electroweak symmetry breaking, because in SMEFT and HEFT that's actually the major difference which we haven't seen yet before. Okay, so that's what I wanted to say, and maybe I can take questions if there are any.
Thank you for the very